Hi class, this is a recorded lecture 31 for Friday class as well as lecture 32 for Monday class. Unfortunately, I have to be out of town for family emergency situation, so what I would do for these two recorded lectures to show you some example on the distribution power flow module that sort of summarize everything that we had since chapter 4, because as I mentioned earlier that we have all the elements considered in the modeling in the very specific detail that can be extracted from the geographic information system, which include topology and all sort of detail. And now we're going to use those information together with the metering infrastructures from each load and to model all of them in real time, so that we can estimate two main things that is of interest in distribution classes. One is to estimate the power loss, as well as to find out what would be the voltage profile for regulation purpose. So I have also emailed you guys about the due date of the homework 6, because I feel that there are some folks who's currently traveling around for business because of the job expectation. So what I do is I postpone it to Wednesday, April the 13th, next week, a little bit 2 days before the exam 3, so that you have a ample time to work together and find out what you didn't do it right for the homework. Hopefully we'll make the same mistake again in the exam. This exams is tend to be a quasi kind of comprehensive exam, because I don't include the first 3 chapter of the textbook, because the chapter 4 actually begin the detailed modeling of those, like as well as the regulator and distribution transformer, and all this combined together. I can actually put it as a one form that you can be used. You can be have a better understanding about what the modeling tool looks like, and how each iteration of the power flow will require you to compute. So as I said, I can't have a distribution feeder without a line, without a load, or without a regulator, because they're sort of integral of those feeders. So what I am going to do, though, in this lecture is to show you some of the example in MATLAB, and then hopefully you get an idea about what are the model you will apply. I feel that the last lecture was a little bit confusing to you guys because of the iterative process, and I'm going to actually talk a little bit about that today, so that you will have a better understanding about the step you require you to go through. Basically, it's not as complicated as you thought. Is what we would go through. This is what so-called backward-forward sweeping. This is a unique modeling for distribution power flow analysis, particularly for the radial and unbalanced aspect of this, because I mentioned last lecture also that the transmission system is presumed to be balanced, and then we, as a result, we use per phase instead of 3 phase for simplicity of the analysis, for memory efficiency purpose, as well as to because of the nature of the transmission system is in the mesh network, so we consider everything as a whole lumped together and model is as in the Y matrix for this iterative load flow analysis. So principle, they both are the same, but we have a better approach to deal with in distribution network in order to assure that we have the better conversion, better chance of conversion, so that we will get a solution. Without having a solution for load flow, it's meaningless, because you can't have accurate numbers of voltage at each node. That means you may not be able to also estimate how much loss that you would like to know per feeder. So that's the kind of thing that we are going to talk about that in this small example. And if you plan to take a distribution tool in the next fall, then you will have a more chance to deal with a much more complex distribution feeder, which we will extract that from the GIS dataset instead of simple tree node with different combinations of load and regulators. this slide give you a projection on the number of classes we need before we get to the exam review. So today I'm going to give you some example for MATLAB, and then the next lecture as well. And then when I come back on the Wednesday next week, I hope that you guys will have a better understanding about what this is would be, and hopefully will ask me some question that may help you to prepare for the exam. And as usual. Usually what I did was for the exam review, I will talk about some key issue, and then leave the rest of the time for you guys to ask me questions about what to expect in this exam tree. So this is one of the figure I drew some time ago, and I thought that to be able to give you some perspective about how complex the system will look like when we go through the backward forward step. So here's the thing. This is a way how we go through the backward step, and then from what we call children node 8, 9, 10, 11, 12, 13, 14, 15. This is a step will go concurrently all the way to this level 3, level 2, and level 1. And until we get to this point, then you will have the forward step. So this is a forward step and backward step. As I enumerate all this forward step here is 8, 9, 10, 11, 12, 13, 14, 15. And then later we'll go 4, 5, 6, 7, and then 2, 3, and then 1. The reason we have to go through this sequence is that this sequence will allow you to have information you need here before you compute the sum of this current at node 4 as well as node 5 and node 6 and node 7, because for example for node 5, without computing node 10 and 11, you can't find out what is the total current you need. As I said, for the backward step, you need to initialize the currents from the backward step, and sometimes you also can use incorporate the voltage profile as well. So that's the generalized A, B, C, D matrix that you need. For the forward step is just basic A and B matrix you need. So each of the two terminal element, like for example, if this is a distribution line segment, then you have actually going to go through this chapter 6 to find out the generalized matrix C. If this is a regulator, then you will have to go back to chapter 7 to find out the appropriate model for this two-terminal element. If this is a distribution transformer, you have to go back to chapter 8 to find out what exactly the specific distribution transformer configuration would be. The beauty part of this generalized matrix is that no matter what type of element you have, you just have to stick with treat it like a black box, as I said earlier. So that black box will allow you to convert efficiently from right-hand side to left-hand side for the backward step, and then for the forward step from left-hand side to right-hand side. And as you know, the flow of power is still coming from this feeder head, power flow direction. So this concept is very important for you to understand it later, so that if I will have to include the 16 node right here, the 16 node doesn't have to wait for all the 6, 7. Now, if I include 16 node, then the node 3 have to wait for 16, 7, and 6, 7, and 16 node to have a value before I have to compute nodes 3. In order to compute 6 and 7, I have to wait for 12, 13, 14, 15. So you can see that this is sort of like a reverse breadth first search kind of navigation. If you know what I'm talking about, computer science language, is that you have to actually wait for 12, 13, 14, 15, 6, 7, 16, then 13. And in order to get into 1, then you have to wait for 2, and the same process you get through this for each level of navigation, so for each node. So that's the principle that you have to understand. So for each step, you have to understand what are the things you need to get I and V and so forth, from left-hand side all the way to from right-hand side all the way to left-hand side and vice versa. So a backward and forward step consider one iteration. So I will say one iteration have backward and forward procedure that you have to go through. And then you have to check the threshold of the tolerance for every node, and if that's exceeds the maximum tolerance you need to find out. Typically for conversions power flow, you might have less than 10 iterations to go through this iteration. So you will have to go from right, left, right for one iteration for 10 times or less, so that until the tolerance value has been less than what you computed, then you stop the process. So this is a very important step that you have to understand it before you actually get into the detailed model, which I will talk about that next. So here is another simple example, is that it's less complicated than before, but the same principle apply. Is that if you want to get, let's say I'm going to name all this with node number 1, 2, 3, 4, 5, and 6 node, then you I'm sorry, this should be 6, not 7. 6, 5, 4, 3, 2, 1. That is a backward step. 1, 2, 3, 4, 5, 6. That is a forward step. If you only have load 3 load here, so load 1, load 2, load 3 here, then the step is pretty simple, right? So you have this IN to have to find out what would be the value of VM times C plus D times IN. Now this black box, I call it black box because it can be any element. That's the reason why I asked you guys to summarize the distribution transformer chapter for this, for every distribution transformer we will consider for the next exam. Because if you do that, and any type of distribution transformer is given to you, then you can simply pick this and do a computation of converting information from right-hand side to left-hand side. So this black box could be anything, but indeed, if you have load, you have current, right? And the initialization step, for example, especially for the backward step, the voltage will be used with the nominal value, and then during the forward step, you will correct that voltage value from the sum of the current at this node. So you can see that as you progress from 6 to 5 to 4 to 3, if this is 1 kilowatt, and this is 1 kilowatt, and this is 1 kilowatt, then this remain 1 kilowatt all the way into the form of current. If you want to use it as a constant power, you still have to convert everything into current. Then and the basic formula will be I equal to S over V conjugate, and so you have to consider that in per phase, so that I is actually 3 by 1 size of a matrix. So you add them out all the way to the end, then you will have, when you have the current right here, you will have current for load 1, load 2, and load 3 combined together as a whole. So that's the another scenario about how you will look at the backward forward step. For these two lectures, the Friday and the Monday, what I will go through is the MATLAB example, of course the illustration for problem 10.1 and 10.2 of the textbook. So the way how the author write the material of the textbook is that there's a lot of information depend upon the previous chapter, but I think that this is a little bit longer question than we have before, so because you need the detail of each kind of element in the system. So for problem 10.1, actually what we are considering here is the powerful problem in the set required application of modified lateral techniques. Students should be encouraged to write their own computer program to solve the problem. So this is a problem statement that you might see on page 371. And I suspect this problem may apply to all of the questions for chapter 10. So the only difference is that the auto might change different type of transformer, regulator type, or the other kind of transformer in a different way, so that you will exercise applying a different generalized matrix A B C D and capital A B into this similar problem like this. So you have node A B 1, 2, 3, and 4 the most. So this is a 69 kV network with a substation transformer. This is a substation transformer in 5,000 kVA, so it's about 1,000 times than the typical distribution transformer in the delta grounded Y connected fashion, 69 kV to 4.61 value. I think this is probably 4.61 value that we have. And so they give the phase impedance matrix with the 4 wires. So this is actually already reduced into 3 by 3 matrix. So this is good to go, except that you might have to multiply that by the distance you need. And then the secondary voltage of the infinite bias are balanced, are being held at 69 kV for all power flow problem. So infinite bus, usually what we refer to as an external equivalent circuit to the transmission network. So this is the way how we describe in the system. And the 4-wire Y feeder is about 0.75 miles long. So this is from node 2 to 3 is probably close to a mile long. And unbalanced Y connected load is located at node 3. So they have a different kind of loads that we have. And then has the following value. Phase A, B, C, well, you have 750 kVA at 0.85 lagging power factor, 500 kVA 0.9 lagging power factor, 850 kVA 0.95 lagging power factor. So you will have to make sure that you convert this information into the current. So apparently, I guess this is telling you that this is a constant power problem. So to convert this per phase into a single phase 3 by 1 matrix, you will have to use that matrix I2 to S over V conjugate to compute each phase of the information from this table. And then the load at node 4 would be this, is 0 initially. So apparently what the author would like to provide you more insight is that they are trying to have you compute the load without specific distribution transformer, and then probably later on they will include this distribution transformer here for this probably the Y and delta connected configuration. So you will have to go to the table that you have, what is the generalized matrix for A, B, C, D, and capital A, B for this specific Y to delta connection. So these are all the information you probably see from example from the textbook, but I will leave it up to you to actually go through it one by one. I think the author did a pretty good job in putting all this detail together in the chapter 10 material about how they go through the process of computing the power flow analysis. So the whole thing here is that for 10.1 is for the system as described earlier, and assuming that the regulator are in the neutral position, determine the forward and backward sweeping matrix for the substation transformer and line segment, and then use a modified ladder technique, which means this is backward forward sweeping technique, to determine the line to ground voltage at node 3. Use the torrent value 0.001 per unit, give the voltage in actual value in volt and on the 120 volt base. So what we have here is also the regulator. So I'm going to go through this MATLAB in detail about how to show you the step for the 10.1, at least in these lectures. in the way how you write the MATLAB script, most of the time that what you have to do is to think about what you want to initialize all this variable. So as I usually do is clear out all this variable and clear the screen, and then so that you have a clean slate to begin with all this scripting. And I'm the person that always want to visualize things, so I always like to draw things like this to show you the configurations of the node 1, 2, 3, 4, and then specifically what are the things that we need to initialize. So you have the substation transformer for phase impedance information right here, and then you have the substation ratio right here, right here, and then the line information in line. So these are already given in the statement of that problem before even 10.1, as I mentioned earlier. So so you don't really have to actually go through the specific detail about how you form this GABC matrix as what we did for SM2, but you will be given that already. And given the unit that you have, ohms per mile, so you probably have to multiply this value as well, which is a distance of 0.75 miles, because that GABC unit was in ohms per miles. And then the power measurement that you have. So this is the one that I mentioned earlier, that you have 750, 500, and then 850 kilo. So don't forget the kilo when you do calculation, because that is 1,000 times different. And then you have the power factors of this per phase. Convert those information into complex power form. So I think this is a pretty clear that how you learn how to convert this. So the cosine, arc cosine, and then lagging indicate the plus sign here. So that's how you get the 3x1 matrix for the S. And then this is a D matrix that we have before. That we learned it before. It's converting line to neutral to kind of phase conversion between the two. And then the U is actually in MATLAB, you can actually write diagonal of 1 3x1, so that you have 1 1 1 0 0 0 0 0 0, something like that. This is equivalent to that. And then also another thing that converting, so nominal voltage line for delta connection, and then as I said before, in circuit you have to convert that everything to line to neutral, which is a phase voltage. So this is what I did for converting the nominal voltage with the 30 degree and so on and so forth. So now 10.1 page 354. This is a second edition, but I use the same script as before. So the first question is pretty straightforward. You initialize this is very similar to the SM2 that I asked you to do this, which was I think there was almost close to 22 free point for you to just show me what are those individually for those generalized matrix. So A, B, C, D, and capital A, B. And apparently this is a modified line model, not an exact line model. So we got that initialized for the line, and this capital Z line here I have is already including the distance information. So we are good to go. So this is in ohms instead of ohms per mile. So that was it for 10.1 question 1. And then for 10.1 question 2, they asked for some more other thing. So here's a little calculation that you might have to know. So as you can see, that initialization of what we had earlier is just for the generalized matrix C. But now, to be specific about this backward forward sweeping powerful analysis, we will need the current. So N and N is the zero value that we have initialized, which is 3x1, and then this is the O value. And I make that error iteration to 99,999 because just to max out the value so that we will have a reference for us to say what are the error tolerance value and so on and so forth. So I equal to 0, so this is a while loop. We have to go through it, and you know this while loop will include backward step and forward step, right? So this is an iteration between the red area as shown here. So 3 and 2 and 2 to 3. So what we do, V3, how do you get V3? That's how you compute the V3 based on the currents, IABC N, which is from this N, right? And then the voltage, which is the nominal voltage here. And if you trace out the screen out, the IABC N is somewhere. Let's see. Here you go. I think this is the initialization value and the voltage. So pretty much that you have the voltage value already, and then you save it in the magnitude form because you're going to find out the errors, right? So the V1 and V2 is already saved here for these two elements, 2 and 3. And then to find out an error for the new and the old, you simply do this absolute value divided by the V nominal value and see how much that errors go. Right. At the same time, the backward step is also including the current. So you have the IABC N to get to this point, N, which is node 2. Actually, M is still node 3. Node 3. Then you have a conjugated your S value divided by V3, which is the initial value that you brought out from that little small forward step here. So you put it right here, and if you see that the S value is actually coming from what we initialize here. So the way how the author wants you to appreciate the iterative process by focusing only for the node 2 and 3, so that you can see that the process of going through this iterative process will be much more intuitive, in a way that you have initialized the value of this tree from this load, and then you have to move this in value to node 2, which is IABCN, so that you only have use, which is in this case is the D value times the IABCN, because you don't have the C value, because this is not an exact line model. And then you get the absolute IABCN value, and then you update the voltage and increment the I iteration. So you're going to go through the second iteration and repeatedly go on and so forth until the errors sort of be more than less than what the torrent value. If you set the torrent value to be this small, then this will go through as many times as possible until it reaches this criteria with the torrent value, with the error less than the torrent value. As long as the error value is more than torrent value, this loop will keep repeating. And by the way, it may keep repeating forever under this circumstance, because if I would have to, only if I put this all situation when I have to include that I will halt this process after 100 times, because I know that it will never converge, which can happen sometime. So this is what for the question 2 power flow analysis. So gradually, what the author have done now is to extend node 2 to node 1. As you can see, visualizes from 3 to iterative. Then you're going to include a regulator model, which is sort of in the substation level. So the same thing that you have to do is to go through this initialization for the voltage regulator to find out the PT-CT ratio for the regulator and the load center where you want to set it, which is based on G equivalent value, and then start the computation about finding out what you need for the compensation impedance setting. So this is question 1 for 10.2. So I think I'm a little bit running out of time. For the next lecture, what I would like to do is to go through 10.2. But let me summarize this a little bit for 10.1 problem. So the 10.1 problem is pretty straightforward and a little bit easy because the author wanted to make sure that you get through this step of initialization first before you get to the more complicated situation, like we include more regulator and maybe also including distribution transformer type and so on and so forth, and then as well as the power transformer in the substation. Then then the complicated process might increase more, as I'm just briefing you through it more in detail next. But those are the things that you will have to know for sure to find out the calculation. So with that, I am going to stop here for Friday lecture, and then I will talk to you more about 10.2 for Monday lecture. Thanks.